I'm Dr. Kevin Howard. I'm here to talk to you about the prospects of nuclear power and how it can contribute to net zero targets by 2050, if it can do that. This is an update to material that I presented, as you said, in 2021. And I'll go through how the data has changed since then and what the progress in nuclear fusion particularly has happened since then. Quite significant. So this is me. I am a systems thinker, I like to call that. Systems engineer to some people. I call myself that now. I think people get turned off sometimes by the term engineering, but I've been an engineer for 50 years, so yeah. I have got a degree in electrical electronic engineering, a PhD in optimizing complicated systems. I realise that most of my problems are people, so I've also got a postgraduate qualification in psychology and a diploma in business and finance. Now, I teach people how to solve what some people call wicked problems. I teach around the world. I have worked with the Atomic Energy Authority in the UK. I helped them set the strategy for something called STEP, Spherical Tokamak Energy Project, which I'll talk more about later. I've also taught engineers from the Tokyo Electric Power Company who are responsible for managing Fukushima and cleaning it up. So I've taught them how they solve some of their really, really wicked problems there. Whether they can or not is still to be seen, but I'll talk a little bit about that too. F4E, Fusion for Energy, is a company that's UK based but is helping European support for fusion developments, and I work with them still, and I've taught many others how to solve wicked problems like this. All this material today is based upon open source material, anything you can find on the internet. I'll talk about what that information is, where it's come from, what its heritage is, whether it's credible or not. I'm trying to ensure we are not biased in anything we do in our decision making. That's really what I'm here to do. Make sure we look at it fairly and honestly. And will we achieve net zero as a result of that? What does that mean for our electricity generation in the UK? Ultimately globally as well, but particularly the UK today. And is nuclear energy part of that net zero, whether that's fission or fusion? I will explain the difference between that and how that works and how we are challenged by the two in different ways. Particularly, I'm looking at the future of fusion energy because I think that's the most interesting way forwards at the moment. It's where a lot of research is going on. That should become clear as I go through this. I'll talk about why it's so hard to do this stuff. And there are some really big numbers. That's what really comes into this. And really small numbers. Why is nuclear so bad? I think that's one of the biggest challenges we face. Is we are dependent on nuclear energy. We have been for the last billion years because that's what the sun does. So why are we so afraid of it on Earth? We'll talk about that too. I've got some reality checks. Some things that I think are distorting our thinking and decision making potentially in different areas. We can talk about whether I'm right or not. This is not meant to be a political statement. This is just my interpretation of numbers as I see them as an engineer. And I have updated the material from 2021. So if you were here or were able to see me in 2021, you'll see some of the data I had then compared against where we are now and see where we are going and how challenging that has become. Data sources, mainly the national grid. Has anyone listened to Radio 4 today at lunchtime? There was an interesting piece about smart grid development, which is inevitably part of this. It was the bottom line. So go and find it on the iPlayer. It's an interesting listen about how that is already developing and how it is being forced by the very technologies I'll be talking about tonight in that direction. I've got some material from Department of Energy, Business, Energy and Industry, and from my Institute of Engineering and Technology, and something called Our World in Data, which is an organisation that does some deep mining on data and presents it in an accessible way. It's used by quite a lot of research organisations. It's more reliable than Wikipedia, to be honest. So I've used some of their material as well. And some other things which I'll reference as we go through it. But I'm trying to look deeper so that I avoid bias in all of decision making. So I can present this material as unbiased as I can be. So, how are we going to achieve net zero? You familiar with the government's 10-point plan? 10 points: advancing offshore wind, driving towards hydrogen, delivering advanced nuclear. The third line on there is nuclear. Yeah, accelerating transition to electric vehicles, green transport. That's a big challenge because they tend to be very high consumers. They're one of our biggest emissions. Jet zero, if you're familiar with this, and green ships. That's a really big challenge. There are some very big diesel engines in ships that soak up lots and lots of energy. And green buildings, we know about insulation, but also looking at architecture for new buildings that are much more efficient and potentially net zero from the outset. Carbon capture is a bit of a double-edged sword. It takes a lot of energy generally to capture carbon, so whether it's actually beneficial is another matter. And protecting the environment, which I think at the moment is a very challenging thing to do. And finally, trying to balance the innovation funding across the whole market space. Now this 10-point policy was set by Boris Johnson some years ago. I have seen nothing in the current government that changes that. They are still following the same 10-point plan. I think that's still probably the right way to go. The point really is that they are following it. So I'm going to be mainly focused around item 3 in the nuclear, but I will touch on all of the others on the way because I think you cannot do one without looking at the whole picture. What does it mean for electricity? The National Grid do an annual assessment about what our projected energy usage is across all sectors, not just electricity. They look at gas, they look at biofuels, they look at air, wind, solar, everything, including our interconnect. There are 5 interconnect channels with Europe that we regularly use. So they're looking at all of those things. And for my, until the beginning of this year, in fact, even at the beginning of this year, April, they updated against what they're calling their future energy scenarios, a steady progression without lots of impetus towards net zero, systems transformation, with a lot of hydrogen for heating, lots of initiatives in there. A consumer-led transformation where we all go out and force government to do something about it, which is, I guess, what you guys here are really about. And leading the way, where we bring all of the best together and look at it from a complete systems problem. So the first one, nobody leads, we carry on as regardless. Maybe we'll get there. System transformation is about industrial lead, where they are pushing technologies at us. Some of that is happening already. Because consumer transformation is where we take the lead and we get out there and actively look for greener ways of operating. And leading the way is when we all pull together in the common direction. Now, that all changed in August this year, which slightly threw me because I started updating this in June. But I found new data in August when the National Grid suddenly shifted their future scenario assessments into a slightly different way of looking at it. In an active way of looking at it, I think you would say, where they are actively engaging in making a difference rather than simply seeing what happens and tracking the data, which is what it feels a bit like they've been doing. So they now have 4 ways of looking at it: holistic transformation, electric engagement, hydrogen evolution. Now, I will say one point at this point, almost all the engineers I know believe that the future of energy is actually hydrogen, because that's a very green energy. We can produce it very easily and we can distribute it fairly easily because we have a gas infrastructure which can manage it. And finally, counterfactual, they call it, which basically means see what happens. That is joined up thinking, consumer engagement, hydrogen in industry, and fail, fundamentally. But they are actively engaged in doing it, so they actually now have an action plan. An action plan that looks at accelerating infrastructure delivery, which if we are to pursue electric vehicles, and we desperately need better infrastructure, the smart grid would be part of that infrastructure rework. We need to be smarter in the way we manage the energy distribution, so that's what they're looking at there. We're looking at market reform, where we are driving the innovation funding stream in a way that positively engages net zero requirements. Part of that is the Great British Energy Organisation that they've established now. Prioritising hydrogen, because the engineers in here believe hydrogen is a very valuable asset. As I say, it's easy to generate, easy to store, easy to distribute, and is green inevitably. Not quite green inevitably, because some of the way we make hydrogen is by breaking up methane, which is not necessarily green. It's called blue hydrogen. But we can make it green by electrolyzing water. They want to accelerate low carbon heating. That means pushing us to use heat pumps for our own heating. I have a slight difference in that. It's still a heat pump, but I'd rather go to air conditioning, because that gives me much more flexibility, gives me greater efficiency actually, and because of the way my solar panels work, I can do it entirely off-grid. So that's just personally. Others may need to do heat pumps. Innovation and consumer trust. I think that's something that has been missing in the past, because previously the grid has sort of been following the data rather than pushing the data. Consumers seem to have been left behind a little bit in this. I don't know whether you feel that. Yeah, so they need to work on innovation and consumer trust and make sure that we understand why we should spend all this money on getting solar panels and heat pumps and the like. And there definitely needs to be a focus on efficiency. There is some evidence that this is happening anyway, and I'll show you that in a moment. But it's definitely something we can all be more efficient in what we do if we understand where our energy is really being used. So that's something else I might touch on. Expedite the innovation for connectivity. That's about making sure we are distributing the energy in the most efficient way possible. That might mean giving the national grid the ability to turn off your fridges or freezers so they can save energy at the right time. But that's about being smart about how we use energy at the right time when it's available to us. And finally, making sure people are smarter about understanding energy uses, energy distribution, and we have the right skills in the right places to do the right job. That, to me, is about the most positive I've seen coming out of the national grid for the last 10 years. So I'm really pleased to see that. What does it mean to us for CO2 emissions? This was how we were looking on the 2020 data that I used in my last presentation. They're looking at driving that more quickly and more actively down to achieve net zero. Rather than seeing what happens in these different scenarios, the activities they're putting forward should improve our chances of achieving net zero. I'm not guaranteeing it, but improve our chances. I think it's a good move. Our gas use projections, this is what they were when I last presented this. Interestingly, they've increased because there is an underlying assumption we will continue to use hydrogen to replace our natural gas resources. And it will still be greener for doing so, but we will not have to change out all our boilers. We'll just have to change the jets and use hydrogen for them instead. There was an experiment done in, I think, in Newcastle last year, converting all of their boilers to hydrogen. It wasn't entirely successful. A lot of complaints that the specific energy of helium is not as high, and therefore you don't get the same heating capacity. You have to run your boilers for longer. You need higher gas pressure to achieve it, and that wasn't considered in all of the analysis they did. But it can be done. It can be done en masse without investing lots of money in heat pumps. So they're expecting significantly greater use of gas, but not natural gas, hydrogen. Electricity demand, this is what we were looking at in the 2020 data, their projections. I think these are much more realistic. And you see I've had to push the scale up to the top of the screen to do this. So we're looking at significantly higher electricity usage. That means that's got to be green generated electricity if we are going to achieve net zero. So the push for offshore wind is a significant part of that. I think you're probably aware that the government had a sale of offshore wind last month, I think it was, where they're fairly successful in getting that to the market, whereas the previous government had failed. To be really fair on this, the previous government had set all the rules for this sale too, so all they're doing is turning the handle, although Labour did increase the amount they were selling by 50%. So there's 50% more offshore wind in that sale than there was planned to be. Where's it all going to come from? All this extra energy that we need. This was what I projected, or what National Grid projected in 2020 data. So now, just about continues at this point here. Am I feeding back? Sorry. But significantly higher. The point I wanted to really get out of here, this is, if I go back, that little beige line there is nuclear power, which is pretty much flat. About 3 times more nuclear power in the projections now than there were in 2020, as part of the bedrock of electricity that we will need. There's also a significant part here, which is actually our interconnect with Europe. So the relationship with Europe is significant if we are to achieve this too. And that's actually, that's exporting our power to Europe, which we do now. We balance between ourselves. Today we were importing, and I'll show you some numbers, today we're importing about 12% from Europe. But last month, France had a problem with their nuclear power, so we were supporting them. This is what it means for the expectations of nuclear power if we are to achieve net zero. Significantly increased amount of nuclear power. So the prospects for nuclear power are really quite important to us. What's it mean for nuclear power then? That's what we're here to talk about. This is the sciencey bit now. This is the only equation I'll use, but I think you're probably familiar with it. Yeah. You've seen this before. We have, in a nuclear reaction, we have a little bit of mass is lost. That mass gets converted to energy. It's a very small number. That's 29 zeros after the decimal point before you get anything meaningful. Very small number. But if I multiply that by the number of atoms in a kilogram of material, it's a big number. Overall, it's still only about 0.00, 0.000 something. So still not very much energy. But Einstein also put that number in there, which is another very big number. Yeah? The speed of light squared. So I can get 10 to the 14 joules of energy from 1 litre of water. That's enough to run Wootton Under Edge for a year. Thanks, Einstein. So how do we do that? How do we do that in fission terms first? So nuclear fission, are you all familiar with these terms? Nuclear fission is where we have a very big atom that's fundamentally unstable and it breaks apart. We get bits of different atoms off it, we get some free neutrons, these green ones, and we get a little bit of energy out of it, a little bit of energy in the first equation. Yep. So that's how fission works, and that's what most of our nuclear power at the moment is based upon, fission energy. We also get lots of other stuff coming out of it that nobody wants, yeah? That's the nuclear waste that everyone's so afraid of. I'll give you a number on this, I think, and this is actually not anything I've calculated. It was an activist in America who was really adamantly green and anti-nuclear. He worked out that the total global volume of nuclear waste is the size of a football pitch, 7 meters deep. Sounds like a lot, doesn't it? 7 meters is the size of a 2-story house. Then he worked out that a coal mine produces that amount of toxic waste every day. That's one of the reality checks. The other thing you realise is it's not mostly waste. Mostly it's just his unreprocessed fuel, and it goes back into another nuclear power station if we were building them. So it's not so much waste. There is a big problem with nuclear waste, and I know that my company is working on how we manage nuclear waste at the moment. It really is a big challenge, and I'm not trying to minimise that at all. But we'll move on to fusion and we'll talk about how that generates waste in a different way. So, things that are working in that way, Hinkley C, you know, down the road. Yeah, this crane here is called Big Carl. Have you been down there? He's putting the lid onto the primary containment vessel, which is now closed, I believe. It's potentially going to generate 3.2 gigawatts of power. It was conceived in the last century, literally, when our grid network was based upon a small number of very big power stations distributing outwards to the houses. That's not how we're operating right now. We've got a massive amount of small generators and solar farms, wind farms, and energy is flowing all over the grid, backwards and forwards. I'm not bragging, but last year I exported 1 megawatt hour from my house. My net usage was negative last year. So I'm exporting power most of the time. So we're moving now to what are called small modular reactors or advanced modular reactors that are around 300 megawatts. That's about the size of a good wind farm, and it'll run a small town quite happily. They are much, much cheaper to deploy, install and connect because they don't have big connection problems. They're much more like the systems are working to now. They're much smarter, so you can turn them on and off much more quickly. And actually the advanced ones reprocess their own fuel problems, so they don't generate the same waste either. It's based on Rolls-Royce's nuclear submarine capability, so it's actually UK design, UK funding, UK owned, whereas Hinkley is French design, Chinese money. So let's look at fusion now, the next generation. Fusion is where we take two atoms that are themselves slightly overweight. So these are hydrogen atoms, sorry. Deuterium is hydrogen with an extra neutron. Tritium is hydrogen with 2 extra neutrons. They both occur naturally. There's plenty in that water that I've been drinking. We drink it all the time. So it's naturally occurring, but if you put them in the right conditions and you smash them together, you get helium, you get a spare neutron comes out, and a little bit of energy. Same little bit of energy we got from the last one, from bits falling apart, but now we're making actually quite a useful gas, because helium we're running short of at the moment. Some tritium is produced. That spare neutron goes and attaches itself to some deuterium to make it tritium, but I want that in the fuel cycle, so it's not wasted, it just goes back into the cycle, that theoretically. And even if it doesn't, it's only got a half-life of 12 years, and it's naturally occurring, so it's not really a big deal with it. So that's how it works. Lots of resource out there, lots of water. It's clean, reliable, we get it working, notionally unlimited, much, much safer than regular, and 1 kilogram of fusion fuel is equivalent to 10 million kilograms of fossil fuel. That ratio is what makes it work. So one bathtub of water contains enough fuel for one person for 60 years. Yeah. So that's how fusion can work. So why aren't we doing fusion all the time? Why is it so hard? Fusion is hard because fission happens naturally. Things fall apart. It's called entropy in my world. Fission is critical. It doesn't even start happening until you get to 45 million degrees C. Yeah? We have to get all of these nuclei and electrons broken apart into a cloud of free agents, a plasma at 45 million degrees C. How are you going to contain that? That's really quite hard to do. So we use a magnetic bottle. That's one thing, because they have a charge. They spin within a magnetic bottle and won't escape it, if you can keep that bottle intact, that is. Or we use something called inertial containment, where it's a bit more complicated, where we put pressure on them to keep them in one place and heat them at the same time and make a very, very small explosion out of it. This is the sort of bottle we generally use. It's a donut. It's called a tokamak in this world, donut to most people. That is the picture of the inside of the Joint European Torus. I don't know if any of you have seen that. It's at Culham in Oxfordshire, and it's just been decommissioned because it's been running since 1983 as an experimental European capability, run primarily by Brits, but it's got supported from all over Europe, so there's lots of scientists there running it. It operates at 300 million degrees C. That's 10 times hotter than the sun. So when you talk to the guys at Culham, they like to say, what's the hottest place in the solar system? I say, it's not the sun, it's us. That's why it's so hard. How well are we doing on this then? Well, in 2022, the National Ignition Facility and Lawrence Livermore facility in California demonstrated the first positive output from nuclear fusion, where they put 2 megajoules of energy into an internal explosion, an implosion of material, and they got 3 megajoules out. So that's about 2 Mars bars in and 3 Mars bars out. It doesn't sound like a lot. It all happened in 5 nanoseconds, if you know what that is. Yeah, not very much time at all. And they did it by firing lasers at a pellet about the size of a peppercorn, 2 millimeters in diameter, made of diamond, filled with deuterium and tritium, taken to cryogenic freezing so that the deuterium frosted the inside of the diamond ball, and then they bombarded it with 192 lasers until it exploded or imploded as a plasma. It's not easy. It's not easy at all. JET's last operation in 2023, they ran for 5.2 seconds. So that's, what's that, 3 orders of magnitude? No. 9, 10 orders of magnitude more than the NIF facility was able to do. And they generated 69 megajoules of energy in that time, and they consumed 2 milligrams of fuel to do it. So this gives you an idea of the sort of energies we're talking about and the amount of fuel that we need to do that. That's next to nothing, isn't it? But we've still got a long way to go. A long way to go. What next? Lots of investment. This has suddenly become the big thing in energy fusion. So we have got ITER, the International Thermonuclear Experimental Reactor, although they've dropped that acronym now, they just call themselves the WAY. The STEP, the Spherical Tokamak Energy Project, I worked with the Atomic Energy Authority to set the mission and vision statement for these guys about 4 years ago when they were setting out on this journey. And they're following on from the demonstration that JET gave them, but shrinking it down. They realised if you make it smaller, we can generate the magnetic bottle without the same energy needs. So, a slight digression, JET cannot fire itself up from energy from the grid. The grid can't supply the startup energy for JET. So it has two 200-ton flywheels that it winds up overnight using cheap energy and then runs them down to generate the extra 2 megawatts it needs to fire up JET for 5 seconds. They did say that if one of those flywheels were to get loose, it wouldn't stop rolling until it got to Newbury from Culham. Anyway, Tokamak Energy is working on a new similar sort of compressed spherical tokamak where they're using high temperature superconductors to generate the magnetic fields. And Fusion for Energy are supporting the European contribution to the International Thermonuclear Energy Experiment. Zymer is a company that's spinning out in the US, are trying to take the NIF technology using their bespoke lasers to get even higher laser energy into them, so they don't need 192, they only need 55 lasers to do it. But they're still only talking about peppercorns every time they fire it, so it's still got a long way to go to get sustainable power. I think there is a possibility that if you put the two together, use the peppercorns in something like a magnetic containment, you might be able to feed it and get it going. We shall see. There's lots of others going on across the world as well. Lots of them. They all intend to generate power to a grid by 2040, 2050. So they all have the prospect of contributing to our net zero energy consumption in the time frames we're talking about. We shall see. Interest in fusion is growing exponentially. This is a number of startups in fusion over the last few years. This is US funding in fusion in the last few years. It's happening, and this is since I talked to you last. Last year, $6.2 billion into fusion research. So scientists think this is the future for nuclear power. They don't want to build more fission reactors, they want to build fusion reactors. So, next question is, why is it all so bad? Do you know where this is?
Chernobyl.
Yeah, it is Chernobyl, yes. Yes. Accidents, radiation, evacuations, all a challenge for historical nuclear power. These are some of the accidents that have made note over the last 50 years or so. When we were learning about it, the early ones were really quite bad. This is interesting because Russia still estimate 8,000 deaths according to this, but actually the total number of deaths from all sources were only 6,000, so I don't know where the extra 2,000 came from in their study. It's difficult to know. Wind scale fire, they estimated 100 to 240 at the time, but research since has seen no increasing evidence of increased deaths due to radiation. Oops. 3 Mile Island, that's a big deal in the States. Nobody died. There's no evidence of any radiation leak causing any increased deaths at all from that. Chernobyl, 45 people died, mainly because they were desperately trying to stop things getting worse, and they intentionally went into the hottest areas, sacrificed themselves for it. But still, UN estimates 4,000 additional deaths from cancer as a result of the massive radiation leak from Chernobyl. It was by far the worst incident we've ever had in nuclear. Fukushima, nobody died as a result of the accident. One person died about 5 years later from lung cancer from the radiation that he suffered at the incident, but only because he volunteered to go back in to measure the radiation levels. So, why is it so bad? The controls we have in place for nuclear power these days are phenomenal. Appropriately, don't get me wrong, but they are phenomenal. Probably the safest place you could be. In fact, Chernobyl is now the third biggest nature reserve in Europe, because nature will take it back very quickly. These are all fission-related problems, not fusion-related problems. So last time I presented this, I showed you this, which gives nuclear as the third safest, possibly the greenest source of energy in fission. It's now the second greenest and probably the safest, the second safest and almost certainly the greenest source of energy we could have. And that's still based on fission, not fusion. So why are we so scared of this? Yeah, it's a challenge. The numbers don't support our fear of it, if I'm honest. In fact, quite the reverse. So some reality checks. UK is or was the leader in fusion development because we've been running JET, which was for a very long time the only place you could do fusion in the world on a decent scale and experiment with it. I think we have probably lost the lead now because of the investment in the US has gone through the roof. UK upped its investment to 220 million over 5 years, the same year that the US increases to 1.4 billion a year. So we still have very good record in doing this, but we're probably losing it. The ITER is expected to cost $20 billion to make, but is not expected to generate any energy. That's a lot of research funding. It's now finished building its superconducting magnets, but for many years it was taking the world's supply of niobium to make its superconducting magnets. They weigh 500 tons, I think, something like that. Massive magnets. It's a really big beast. Yes, UK invested its 220 million just as the US increased its to 1.4 billion. Now, I do remember what that stands for now. Fusion Energy Scientific Advisory Council, who advise the US Department of Energy what they should be doing in fusion development. So they recommended 700 million a year and they got 1.4 billion. That's the difference. Reality checks. BMJ estimate that there are 1,100 deaths a year from cancer because of radon. So we live in a radioactive country. Yeah? Originally at Fukushima, they estimated 473 deaths attributed to the stress of the evacuation from Fukushima. Not from the explosion or any of the problems or even the tsunami, but just from evacuating the area around Fukushima. In fact, I've also seen estimates between 1,600 and 2,300 died from the stress related to being relocated, potentially unnecessarily. So it's a challenge. The other challenge I have is from solar and wind, and this was a discussion again today on the bottom line, was the need for storage, because solar and wind are notoriously unreliable. Now, I wish I could remember what that German word was for when there's no sun and no wind. Yeah, say? Yes, that sounds like it. You were listening to the programme. Yes. So we need batteries. We need some way of storing all this energy. One of the potential ways of doing that is now hydrogen. That's been pushed quite significantly, but right now we're pushing batteries. Yeah, lots and lots of batteries. This is a Tesla farm in Australia, 129 megawatt hours. That's about a tenth of what we need in the UK. There are currently 93 battery storage farms in the UK of the required 1,145 sites. That will cover 4,000 acres. That's probably not much compared to solar farms, to be honest, but it's still a big amount of battery storage needed. So we've got a long way to go to even manage our wind and solar capability at the moment. Yeah. 1 ton of lithium from the lithium triangle it's now called. I think it's after the rhubarb triangle, but it's a completely different place. That's Bolivia, Chile and Argentina, where they flush lithium from the rocks using brine and then evaporate the brine out to get the lithium. It takes 2.2 million litres of water to get 1 ton, I should say 1 ton of lithium, 15 tons of CO2. So when you're getting all these batteries, we tend to defer all of our CO2 to another country. And I think that's what we sometimes forget about with all these systems we're putting in place. They're not as green as they like to be. The waters around Fukushima, even after they've done the latest discharge of their water, which is actually only contaminated with tritium, which so is that water there, has got 7 to 8 becquerels per litre of radiation, which is lower than the global average for seawater. But it's a political football. That's why it gets the headlines. Manufacturing an EV vehicle produces 80% more CO2 than manufacturing an ICE vehicle. So you need to drive your EV for at least 150,000 miles before you even break even. I was going to put something up here only because I like old cars. I think the greenest car on the planet is a Volvo P1800S, which has done 3.26 million miles. And is now in the Volvo Museum. Yeah, the guy who owned it, sadly he died in 2018, he said he did offer it to Volvo for $1 a mile, but they declined. Monday the 5th of April 2021 was the greenest day we have had, and I cannot find a greener day. When it was a bank holiday Monday, so nobody was doing anything, they were all lounging out in the sunshine, it was sunny, it was windy, and we were just running on sun and wind and gin and tonic, I guess. So that worked really well. 2020 we were running at 46 grams of CO2 per kilowatt hour generated, which is pretty good. April 24 was the greenest month we've ever had at 92.2% green energy supply. I looked this morning, this is hot off the press, so this morning's number. I don't know if you know this website at the bottom there. You can look at this and it will tell you what our current energy mix is at any time in the day. Live data. So this morning we had 36.8% wind, 20.9% gas, 13.3% nuclear. Interestingly, we were running at 12.4% interconnect. That means we were taking energy from France, from Denmark, from Norway. And I think we were exporting to Germany, bizarrely, so we were just shipping it around the place. So that's where it comes from. But we were not using any coal, which is good. But still 20% of fossil fuel, 20% gas. I think we were running about 103 grams of CO2 per kilowatt hour, because that's also on the website. You want to check it out. Yeah. Still got a long way to go then. Conclusions. I think we're pretty well on time. Costa Rica, if you want to go to a green country, runs at 98% renewables for all its energy uses. Sweden hit 50% renewables in 2022. They're on target for their net zero projections. Yeah, UK's world leader in wind generation, offshore particularly. So we are selling the technology, and I think now that we have got an initiative to actually actively develop that, we will see that going further. 2023 is our greenest year, and we're still getting better. So I expect, given the numbers I showed you for earlier this year, when we get to the end of it, this will be our greenest year. It's been a pretty horrible year, if I'm honest, but it still might be our greenest year. We are currently ranked 6th in the world for renewable use. Not too bad for a little country off Europe. British Energy, Great British Energy, Ofgem and the National Grid are now strategically aligned to actively manage our intent towards net zero. That makes me feel a whole lot better about our prospects of actually achieving it. And that's happened in the last 3 months. And National Grid are now actively managing the smart grid so that we can start using these technologies much more smartly. Nuclear power, fission and fusion are part of that mix. We have to accept that. Still got a lot of work to do, but I think we've seen a gear shift in the coordination recently that is reassuring, for me at least. 3 Mile Island is back online. Did you know this? Microsoft signed a 20-year deal to take energy from 3 Mile Island from 2028 to support their data centers and their AI initiatives, because they are big, hungry things. So, do you know this? 1 gigabyte of storage in the cloud will take you 15 grams of CO2 a year. Just trying to open eyes to where the CO2 is really going. Thank you all very much indeed. I hope you enjoyed that. Hope it was informative. I'm happy to take questions if you'd like to. I haven't mentioned them, mainly because this talk was meant to be about nuclear. They are in the numbers, if you look in there. Certainly biomass is in the numbers. There's a little bit of hydro, which covers tidal in there, but it's 0.3% of our generation capacity at the moment. I haven't looked into tidal at all, to be honest. It's a really difficult thing to do. It tends to have quite a big environmental impact, if I'm honest, because it messes up tidal flows, and they're essential to sea wildlife mostly. So I haven't touched on them because that wasn't what the objective for this today was, I'm afraid.
Germany has turned away for political reasons from nuclear, and as a result I think it still has a lot of coal-fired power stations. How is Germany intending to square that circle?
I honestly don't know, because they were very heavily dependent on Russian gas. That's how they were generating. That pipeline's been turned off and they've turned on their coal again. I don't know. France is probably supporting them a lot with their nuclear capability right now because the interconnect works all round. I think they're going to have to bite the bullet and turn on the nuclear again, personally, and accept the numbers, because the numbers are telling us it's not as unsafe as people believe it to be. At the moment, it's in what's called the pond, which is in Sellafield. And, sorry, I'm not answering questions again, am I? The waste is being managed, in the UK at least, in Sellafield. And I don't really know the answer. I know that there are about 5 deep burial sites that you're currently looking at for that. The process they're focused on is what's called glassification, where they bury the material in solid glass, which is deemed to be the most reliable way of containing radiation leakages. But it's still work in progress, to be honest. I still think it's a challenge. I still think we could do more reprocessing and reuse of the fuel that's still buried within that waste, but we're just not there yet. I think it's more current than that, if I'm honest. I know that UK Atomic Energy Authority are actively looking at how we manage waste right now. We've got active engagement in manage how we control leakage, particularly because we've got a 200-year management cycle for this. It isn't something you can bury and forget. So it has to be done with controls, with monitoring, with everything else, particularly if there is the potential of water table contamination, which is one of the critical issues. However deep we bury it, it's potentially going to come out somewhere. I could argue that actually radon's coming out of the ground all over the place, and we're suffering radiation, as you saw in the map, all over the place. And the chances of it ever exceeding those levels is very, very slim. So again, we may be over-fearing something which isn't actually such a problem if it's managed appropriately. But I think it's a more current one than a futures problem. We have to deal with it now. The best way to deal with it for me is fusion, because it doesn't generate it. Yes. I haven't seen any active pursuit because most of the investment right now is going to fusion, not into going back to fission. Yeah, it's one of the options then. And it depends on what the cooling mechanism is, whether it's most of ours are pressurized water cooling with indirect exchange to the generation sites. I certainly know that the original reactors were built in order to generate the purified uranium for the bomb in the 40s.
And to answer your rhetorical question,
yes,
about what are we so afraid of,
yeah,
the words get used in energy and in bombs, and that's not true of solar.
No, indeed.
So,
no.
Which is, and not to say that it's correct to be afraid of it, but,
I'm just looking at the numbers. I know exactly what you mean, and historically, and then to a significant extent, media have not really helped that, because 3 Mile Island became a big deal, but nobody actually died from it, and the radiation never changed anything particularly, and it's going to be fired up again in 2 years' time, so 3 years' time.
The reason why thorium reactors weren't the first ones that were done is that thorium is what's called a fertile material. It can't directly be used as a nuclear fuel. You have to have it's a bit like you need an ignition source to start a fire. So we needed either uranium or plutonium to drive a thorium reactor, and at the early days of nuclear power there wasn't any driver. That's why thorium has always been considered to be further down the line rather than an initial nuclear power. Could I possibly follow that with one comment?
You can, if you wish.
I thought your presentation was wonderful. I agree with at least 99%.
Well, that's reassuring, thank you.
The only thing, just sort of for your consideration, is that I think you're a little bit negative about the future of fission, because there's a tremendous amount of effort going on around the world in new types of fission reactor. Well, I say new types, all the fission reactor types were invented in the 1970s. Yeah. So there is a complete fleet of fission reactors, most of which are far better than the model we're using today, the pressurized water like Hinkley Point. I mean, one astounding statistic is that Hinkley Point wastes 99% of the fuel that is mined to fuel it, and it wastes 2/3 of the heat. A nuclear reaction produces heat, not electricity. So a lot of the cost and engineering is actually spent on putting heat out into the Bristol Channel, which of course is no use to anybody. So the obvious thing with nuclear, whether it's fusion or fission, is to use the heat rather than generating electricity, because a lot of industrial processes and even generation of hydrogen, yes, you can split water, not with electricity, you can split it with heat.
Absolutely. Yes.
So there's nothing to stop a reactor being on an industrial park with a hydrogen generation facility where the heat comes directly from the reactor to split the water and produce the hydrogen that then is piped around the country. I mean, those sort of, if you are prepared to think laterally and are just a little bit beyond the sort of huge power stations at Hinkley Point and electricity and that, if we're prepared to think a little bit laterally, then obviously there's a lot to be gained.
I do agree with you in terms of the alternatives for fission. I think the small modular reactors that are coming online, particularly the advanced modular reactors, have real potential for very safe, localized generation and even combined heat and power systems, which will be much more efficient recovery of energy from them. Yeah, they have a real potential to do that, and I think we'll see SMRs coming online relatively quickly because they have so much smaller investment in a technology that's fairly well established and proven to be fairly safe. So I do agree, fission has a future. I'm not trying to dismiss it completely, but I think the investment right now is going into fusion.
I saw mention in the last couple of days of some sort of articulated lorry mobile type nuclear reactor for the American battlefield. I mean, how small can these things go?
Well, if you take the small modular reactor, they're fitted into submarines. Submarines are fairly big, but you could probably get them into an ISO container relatively easily. Yeah. So they are very easy to deploy in that configuration, if that's what you're looking for.
And there was again, it's one of these LinkedIn interesting engineering things that I spend more time than I should do reading, really, I suppose. But there was also sort of a small nuclear battery that they were, I'm sure, unless my memory's playing tricks on me, that it was something that was likely to last for quite a while, but as a cell battery almost.
We may have some, you may have more.
Can I answer that question?
Yeah, please do.
Beg your pardon. One of the ways, there's nuclear fission and reactions, which obviously are the way we produce power in a power station.
Yes.
But when a radioactive atom decays, it produces energy. So, for example, the waste from nuclear power, which is radioactive, produces energy. So you can put the nuclear materials effectively into a battery. And originally, when the moon program happened back in the 1960s, and the chaps drove around on the moon in those buggies, if you remember that, they were driven by plutonium-238, which is a radioactive isotope which was made on Earth and transported to run the buggies around the moon. The current interest is in a different isotope called nickel-63, which can be made from putting nickel, specially prepared, into a nuclear reactor. And this generates something which can then make a tiny little battery like a button cell fit in phones.
That would fit with what I thought I'd read, yes.
And of course the advantage of it is that it would last for 50 years without charging. So that, and if you think about the safety implications of that, when you use your mobile phone, the one time you need it, when you're in trouble, what's going to happen? The battery's flat, isn't it?
Yeah.
That's the real problem of batteries, whether it's for the grid or for your phone or anything else. The wretched things don't store enough energy. But with nuclear, of course, the isotope is able to provide the energy for 50 years. So your phone would never have to be recharged. And then that comes back to the other point you make, which is, why don't we all have that? Because obviously the radiation can't get out of the battery, it's all sealed into the reason we don't have them at the moment is people are afraid of it.
Yeah.
Not because they'd only sell so many and then nobody else would want them.
Well,
never being cynical, of course.
No, things can change, and,
Yes.
and of course, when you really need these applications, like in space, you've got to, and it's absolutely no use trying to pretend that a lithium-ion battery is good enough for what you need in space. You need the proper stuff.
Slightly off-piste. I have a memory, again, somewhere I was told that a wind turbine actually takes more energy to make than it will ever generate. I mean, is that correct nowadays?
No, I don't believe so. No. Certain early ones where they were less efficient, I guess, possibly, but not these days, no.
If I might just on that. The only thing that people have not really considered properly yet, and I'm a waste person, I deal with nuclear waste, is the waste from solar energy and the waste from wind turbines.
Yes.
And the world is going to, here is a really unfortunate statistic. In America, it costs $1 to dispose of a solar panel in landfill and $25 to recycle it. So can you imagine what's going to happen? Which is, there's plenty of space in the United States, and the whole, in 25 years, acres and acres and acres of dead solar panels.
How long do they last?
25 years.
At the moment, all you can really do is think about where you're going. Well, I'm trying to give you some pointers about where you need to think about it. So when you use cloud storage, for instance, you realise that you're actually prompting Microsoft to open up 3 Mile Island again. And Google these days have been claiming they were green for the last 30 years, and suddenly they're not, because AI is soaking up so much energy that they're not doing that. So when we're looking at all these new things, what I'm really trying to fight against is deferring our needs to an alternative country that doesn't really have the resources to manage them properly. And that's what I'm really concerned about when we're pushing towards lithium and lithium, value of lithium, because we're not selling EV cars as much in the last 2 years. Value of lithium has gone down by a factor of 10 in the last 6 months.
Yeah. It's the same so much in so many of the sort of underdeveloped countries in terms of the impact.
Absolutely.
It's had. But my ancillary question was a bit broader, which is, do we know about what the rest of the world are doing outside of Europe and the US? Because energy has such a massive influence on the whole power base of the world. And Ukraine, obviously Chernobyl, with what's Russia and China doing in these respects?
Well, China had been building a new power station every 6 months or something, mainly coal and gas fired. But I think they are moving towards nuclear fission more now. Whether they are fully compliant with the International Atomic Energy Authority's requirements for those is, I don't know whether that's necessarily true, whether we have full access and transparency to those things. Maybe I'm slightly unreasonably sceptical there, but so we are, I don't know about the whole world. As I said, Costa Rica is 98% green, probably mainly solar. As I said, the experiment that was done in Newcastle had a negative output. They turned it off and they refitted everybody back to natural gas because they were struggling to get enough energy out of the boilers, and the kettles took forever to boil and things like that. So there was issues with it that they didn't like. There's an adjustment to be able to do that. I think the primary thing with hydrogen is actually, from my perspective, it's probably not for domestic heating, it's industrial heating, industrial processes where they can properly configure to use it appropriately. I was in Toulouse last week, and they've got hydrogen buses all over the place. Japan has got a lot of hydrogen cars now, and they've got a hydrogen infrastructure running on hydrogen fuel cells. It's a different way of thinking about it. So when I say hydrogen, I don't necessarily mean for domestic heating, because that's been demonstrated to not work in the way we currently use it. But in the right place and the right time, I think it is a way forwards. Yeah. And not least because it's a storage capability that would replace lithium batteries without the cost and without the impact.
There's a really excellent podcast that I'm pretty sure is called The Hydrogen Ladder, which talks about how actually there are a lot of different uses for hydrogen, and we should solve some of the bigger, more challenging ones before we try and do things on a domestic scale. So maybe thinking about freight and so on first.
Yes, absolutely.
But it's well worth a listen. It's really accessible.
Certainly for transport, it's a positive way forward. Yes.
You mentioned that helium was a byproduct.
Obviously, yes.
Yeah, there is a. I mean, I hadn't realised you could actually make it like that, because there is a shortage of it, as you mentioned.
Yeah.
Because not only does it fill your birthday balloons, but it also is used in MRI scanners and things like that. So, I mean, is that likely to be a viable byproduct?
To be fair, it's not going to be a massive output from fusion. It will generate some, but not in the quantities that we're actually losing it at the moment. I know that it's more difficult to find helium to fill your party balloons these days because we are controlling it now. US were pumping it into caves to try and store it because they were losing too much. And helium is a key resource. It's one of the gases that does escape the planet.
You mentioned the use of water in the production of both hydrogen and nuclear. In some parts of the world and at certain times, water is in short supply. I know we've got oceans are full of it, but the oceans are full of living creatures as well. How big a conflict do you see that poses? Yes.
I see your point, but I see it far less of a conflict than pumping 22 million litres of water into the rock to get lithium out, if I'm honest.
Or making jeans.
Or making jeans, exactly, yes, exactly. And the process for getting lithium in the lithium triangle is rather like fracking, where they pump brine into the rocks and then try and recover it and evaporate it to get lithium from it. So, okay.
I think we'll leave it there. Thank you so
thank you
much.
very much.